Welcome back. How was the remove method? It was pretty tough, wasn't it? Now, I don't expect you to be able to get this. Even for me, it took quite a lot of time to get this working. And I'm going to give you another chance to finish it if you want. I have my code minimized here just to show you the if statements and the steps that I'm taking. So you could always pause this video. But let me just go over the steps I'm going to take. And usually I like coding step by step, but when it comes to this function, it's really hard to go step by step when you're not coding yourself or you don't have a diagram to point to and show. So I'm going to leave the code for you so you can implement it on your own and actually, like I always recommend, draw it out with a piece of paper to understand what's going on. Otherwise, if I just coded this along, it would be a 30-minute video of you getting bored, and then you're not going to have fun with data structures anymore, and we don't want that. So all we're doing is, well, if we remove, we're going to check if there's anything in the root. If there isn't, well, the tree's empty, there's nothing to remove, we're going to return false. Otherwise, we're going to grab the current node as this.root first, and then we do something new here that we haven't seen before. We declare a new variable called parent node. And this is something you may have realized as you coded this along. We need a reference to the parent. Because if we remove something from here, such as 14, well, we need to, before we get to 1, get a reference of 14 so that when we get to 1, we have access to 30 so that we can link 30 to 1. So if we go back here, now that I have parent node variable, and I do my loop to check if the value is less than the current node, in which case I'll go left, and this should be familiar. But this time I'm also keeping track of the parent node. And otherwise, if we need to go to the right, well then we go to the right, but also keep track of the parent node. Now, this is the interesting part. We're looping through everything here and nothing's too crazy until we get to a match. Once we get to a match and we find the current node that we want to delete, we have a match, we need to get to work. And we have 3 options here. The first option is that the current node has no right child. If the current node has no right child, let's have 55 as an example, or let's do 14 as an example. If I remove 14, you saw that all we did was we remove 14, but we kept a reference to the parent node and just moved 1 up. That was nice and easy. And in here with option 1, that's really all we do. We first make sure that the parent node doesn't equal to null. That means we're modifying the root node. Otherwise, the root variable gets updated to our current node. Otherwise, if parent is greater than the current value, then make current left child a child of the parent. If parent is less than the current value, make left child a right child of the parent. Again, I know this is confusing, and like I said, this is something that you might have to go on your own. I'll leave comments out here for you so you can actually play around with it and play around with Visual Go so you understand what's happening. So that's the first option. If that's the case, then do that. If the right child, if we have a right child, but that right child doesn't have a left child, let's find an example that has that. So we have a right child that doesn't have a left child. So that is 54. What happens when we remove 54? If I click on this, 54 gets removed, and we just place 55 instead of 54 now. So in that case, we go, again, check if the parent node is not null, so that we have to replace the root node. Otherwise, we go through similar steps to reassign the node. What about the last option? Right child that has a left child. So if we go here, we have a right child. Let's say if we want to delete 30, that has a left child, 38. So if we want to delete 30 and hit go, we still traverse until we get to the left, and then, oh boy, we do a bit of a magic. This will require you to read through the code, and I've left some nice comments for you so that it makes sense. But we're essentially finding the right child's leftmost child and looping through this, changing the subtrees of the tree. Like I said, this is quite a bit advanced and really hard to explain just on the screen. So I do recommend, if you weren't able to get the remove function, to go through this step by step. I'll link to the code right in the resources so you can play around with this and see that it works. But to check that remove does in fact work, let's say I'll remove 0 from this list. If I click run, I get undefined because there's nothing to remove. But if I remove, let's say 170, and I click run, I get true. And if I traverse our list and try and grab our tree now, let's open up Developer Tools. Paste this, press enter. And now if we go to 9, 20, and we see that the right node is now empty where 170 should have been. So we're able to delete the node successfully. That's enough for now. You can play around with the remove method if you want. You can try and code it yourself. It will take a bit of time. I know I keep saying this. I do encourage you not to get disappointed if the remove method was really difficult. I didn't really want to include it in the course because it is overly complex and not something you want to get too worried about when it comes to an interview. But I thought some of you might be interested in it. Just make sure that it's not something that discourages you. As long as you can do the inserts and lookups, that's what matters for interviews. I'll see you in the next one. Bye-bye.